Purification of water is significant because clean drinking water is becoming a less accessible resource throughout the world. In fact, 1 in 10 people in the world do not have access to clean drinking water. Moreover, women and children across the globe are disproportionately affected by this shortage and spend approximately 125 million hours daily collecting water. Finally, a child dies every 90 seconds from a water-related disease. Now you may be thinking, how can this happen? While it is true that over 70% of Earth's surface is covered with water, over 97% of that coverage is made up of salt water. Two methods to convert this salt water into clean drinking water include forward and reverse osmosis. Osmotic pressure is a colligative property, defined as the minimum pressure which needs to be applied to a solution in order to prevent inward flux across a semi-permeable membrane. In forward osmosis, an osmotic pressure difference between a concentrated draw solution and a dilute feed solution drives water flux across a semi-permeable membrane. In reverse osmosis, an outside energy source is used to generate a pressure greater than the osmotic pressure of a concentrated feed solution in order to force water flux through a semi-permeable membrane. The forward osmosis setup used in this experiment is shown here. The main components of the system include the draw and the feed tanks. The flow rates on the feed and draw sides of the membrane are controlled separately using individual pumps and pressure valves. Moreover, the chiller keeps the temperature of the system constant, and a computer with data acquisition software continually measures and records the mass of the draw tank. As water flows into the membrane, the concentrated draw solution pulls water from the dilute feed solution, shown by the schematic here. Set the temperature of the chiller. Fill both the draw and feed tanks with 2 liters of DI water. Attach the quick-release tubing to the appropriate ports. Select a forward osmosis membrane, such as a thin-film composite membrane. When installing the membrane, it may need to be trimmed in order to fit the cross-flow channel. Ensure the membrane fits appropriately before securing the membrane cell. Tighten the nuts and bolts to lock the membrane in place. Adjust the flow rates and pressures to the first desired testing parameters. Verify that both sides of the membrane are at identical conditions. Allow the system to equilibrate for 30 minutes, or until the mass change in the draw tank is less than 0.05 grams per minute. Add the first saltwater solution to bring the draw tank to a known concentration. Allow the system to equilibrate for 30 minutes once again. Measure the conductivity of the feed tank. Repeat this process for additional trials, increasing the concentration of the draw tank each time. Upon completion, the system must be purged. First, fill both the tanks with 4 liters of tap water, attach the appropriate tubing, and allow the system to flush for at least 10 minutes. Repeat this process for another round of tap water, and finally, with DI water. The system must now be air purged. Set the air pressure to 200 psi. Connect the air hose to each of the discharge tubes. Purge until water is flushed through the system. After, open the cell compartment by loosening the bolts. Remove the membrane and inspect it for any tears or deformations. The experimental setup for reverse osmosis is shown here. This setup is highlighted by a feed tank and a cell train consisting of 3 membrane cells. Water is pumped through the cells at a flow rate set using a pressure regulator and a valve, while the chiller keeps the temperature of the system constant. When the feed reaches the membrane, the rejected stream is sent to the next cell membrane and the permeate stream can be collected, shown by the schematic here. First, set the temperature of the chiller. Measure desired amount of DI water and fill the feed tank. Wet the membrane cells with DI water. Install the reverse osmosis membranes, such as NF90 or SW30 membranes, into each one of the cells. Secure each membrane compartment by tightening the nuts and bolts. Adjust the flow rate and pressure regulator to desired operating conditions. Allow the system to equilibrate for at least 20 minutes. Purge the collection tubes of any air bubbles. Add a saltwater solution to the feed tank, bringing the feed to a known concentration. Allow the system to equilibrate once again. Collect samples from each of the cells simultaneously. Ensure collection times are sufficient for accurate conductivity probe measurements. Also, note the conductivity of the feed tank. Repeat this process for additional system pressures and RO membranes. Upon completion, purge the system with DI water followed by air, similar to the forward osmosis experiment. Open the membrane cells. Inspect the membrane for punctures prior to disposal. For forward osmosis, the change in mass of the draw solution was used to calculate the pure water flux across the membrane. The pure water flux was plotted versus the effective osmotic pressure gradient in order to determine the hydraulic permeability constant of the membrane, A, which is the slope of this line. Next, the salt water flux was calculated using the change in conductivity of the feed solution. The salt flux was plotted against the effective concentration gradient to determine the solute permeability constant. Moreover, we looked at the effect of concentration polarization on forward osmosis performance. Concentration polarization occurs when concentration of solute very close to the membrane is different than the bulk solutions, creating a boundary layer. In forward osmosis, this does not occur on the feed side, as it is pure water. However, on the draw side, the concentration of solute close to the membrane will be lower due to the flux of water entering the draw side. This lowers the osmotic pressure in this region, which decreases the osmotic pressure gradient and in turn lowers the flux across the membrane, hurting the forward osmosis system's performance. For reverse osmosis, we calculated the pure water flux by running trials with only water and collecting the permeate from each membrane cell and recording their corresponding masses. We then plotted pure water flux versus transmembrane pressure for each membrane. The slope of these lines are the hydraulic permeability constants for each membrane. Next, we used conductivities measured in our salt water trials to plot the salt flux versus the effective concentration for each membrane. The slopes of these lines represent the solute permeability constants. As with forward osmosis, we can also explore the concentration polarization phenomenon for reverse osmosis systems. In reverse osmosis, there is an increased solute concentration on the feed sides of each membrane, raising the osmotic pressure. This means a larger pressure must be applied to produce the same flux, resulting in larger energy costs. In the reverse osmosis experiments, we were able to analyze the desalination effectiveness of the system by examining the salt rejection of the membranes at varying pressures. We achieved salt rejection percents between 91.5 and 98.5%. We've shown in these experiments that an increase in osmotic pressure leads to an increase in water flux. We've also shown that an increase in an effective concentration leads to an increase in salt flux. Some of the linear trend lines do not match well with the data. If we were to avoid manually setting the y-intercept at 0, the slope of this linear trend line more closely matches the theoretical value for the solute permeability constant. Overall, our goal was to prove the effectiveness of osmosis systems in the purification of salt water. Although we achieve very high percent salt rejections, these technologies still need to be developed before they can produce viable drinking water and be implemented on a larger scale.